Welcome to Recovering Evangelicals, a podcast for people who were once very comfortable in their Christian faith until the 21st century intruded and made it very hard to keep on believing. I'm your host, Luke Jansen.
And I'm Scott Dyer.
During the 4 years of this podcast, we've heard from 5 different university-trained scholars about fine-tuning of the universe. All 5 of them personally hold a theistic worldview. Last week it was the Christian astronomer and cosmologist Dr. Luke Barnes, and the week before that it was the mathematician Dr. Eli Feder and the physicist Aaron Zimmer, both with a Jewish worldview. 2.5 years ago it was the Christian astronomer Dr. Robert Mann, and 4 years ago it was the Christian theologian, philosopher Dr. Chris Berger. All 5, being theists, well, it goes without saying that they would be quite okay with the idea of fine-tuning of the universe. It fits nicely into a Christian narrative. But what do scholars in this area who are not theists have to say? Those 5 guests told us that their non-theist and staunch atheist colleagues acknowledge that the universe is incredibly fine-tuned. That fine-tuning is undeniable. And in our research we found lots of examples of that. We heard about the staunch atheist Sir Fred Hoyle. We'll hear more about him later today. But we thought it would be important to talk to one of them ourselves and ask how they respond to the data and to that claim of fine-tuning. So today we'll talk to another university-trained astrophysicist on the same subject, but this one describing himself as a card-carrying atheist, who nonetheless is quite on board with the idea of fine-tuning, albeit without a tuner. Dr. Geraint Lewis is a professor of astrophysics at the University of Sydney Institute for Astronomy, where he's also the head of the Gravitational Astrophysics Group. He did his undergrad training at the University of London and PhD work at the University of Cambridge's Institute of Astronomy. Scott, you'll be pleased to know that Geraint also spent some time at UVic, University of Victoria, just down the road from you.
Yeah, wow.
He's published over 400 scientific papers, innumerable articles in the popular press, and 3 popular science books, including this one we looked at last week, which he co-authored with Dr. Luke Barnes. A Fortunate Universe, Life in a Finely Tuned Cosmos. So, once again, the perfect guest to speak to this topic that that we're going to talk about. So, Dr. Lewis, welcome to the podcast.
Hi there, how's it going?
Welcome.
Very well. You're traveling around through Europe, through UK and Paris and Warsaw. Thank you for giving us your time during your holidays.
Oh, it's always a pleasure to talk about physics and the universe.
So, Geraint, tell us about your life growing up. What got you into astronomy?
Well, I was born in South Wales, part of the United Kingdom, and I come from a coal mining country, and so my father was a coal miner, grandfather was a coal miner, etc. I didn't have any basic, scientific role models in my life other than Doctor Who, so I was a bit of a sci-fi fan when I was growing up. But when I got into my teens, I discovered that firstly, I enjoyed physics, like that trying to understand the fundamentals of the universe. And then something strange happened at 16. I suddenly discovered I could do maths. Maths had been somewhat strange up to that point, but then it clicked and I understood how powerful maths was. And I studied maths and physics at school, and I did quite well. And I had no real idea what I was going to do with my life. And my teachers suggested, right, why don't you consider going to university and getting a degree? And I don't come from an academic background. Nobody else had been to university. And I thought, well, why not? And it might open up my prospects for a job. And I went to university and discovered that you can do physics and maths, and you could tie in the physics of the universe, which had that little bit of a tie-in with science fiction aspect. And so again, I started doing the astronomy aspect of it as a physics topic. And again, did well. And somebody said, well, why don't you do a PhD? And then, several decades later, I'm now a professor. So I wasn't one of those kids that, sat there with a telescope and stared at the sky. It's not good having a telescope in South Wales because it's cloudy and rainy a lot of the time. I came there from the perspective of understanding the universe and applying the laws of science as we can understand them to the universe. And I find myself lucky to have fallen in this career. I had no plans to be a professor. I just thought I would have to go and get a proper job one day. But I fooled them all, and I'm still here, several decades down the line.
Yeah. And you must love what you're doing, because 400 papers, that's no small feat.
Oh, well, that's right. I mean, this is the thing with academia, right? I mean, I think if you don't have a passion for the topic that is, your job, then it doesn't work if it's a chore, right? You have to enjoy the subject in front of you. You have to enjoy the finding out of something new. But you also have to deal with the flip side of academia is that sometimes you run into a brick wall, right? But it's part of the discovery process, right? There's no set path. You try stuff, and I've been lucky and fruitful and found various avenues where there's lots of interesting results.
Very good. And one last question, Geraint. I want to confirm, or we need to confirm, in contrast to our previous three guests on this topic of fine tuning, including your co author, Dr. Luke Barnes, you come to this topic of fine tuning without any religious or theological baggage.
Yes, I think I'm officially a card-carrying atheist. I dabbled in religion as a teenager, and I was one of those that exposure to science, etc., flipped me into what I am today. So, writing of the book with Luke, I brought the atheistic aspects to the story.
Hmm.
Okay. So, Geraint, you've written many papers and co authored this book with the title A Fortunate Universe, A Life in a Finely Tuned Cosmos, on the idea that the universe is finely tuned. In what ways do you see this universe as being fine tuned?
Okay, so you have to be very careful when you go around defining fine tuning. Some people are very sloppy with regards to what fine tuning means. And this is something that Luke and I wanted to stress when we wrote the book about what fine tuning means. Some people think fine tuning is something about us, and it isn't really. We're a consequence of fine tuning. But so the fine tuning of the physical laws, essentially, that we have our laws of physics. There are aspects of our laws of physics that we cannot determine from mathematics. Okay, so we have our laws of physics, laws of gravity, etc. We have the mathematical structure, but there are numbers in there. They're the fundamental constants. And mathematics doesn't tell us what those numbers should be. So, like a famous one is, of course, the speed of light, right? 300,000 kilometers per second. We could write we normally use c to represent that. We could write that into our equations, but our equations are completely sterile until somebody goes out and measures the speed of light, and then we can put that number into our equations. And those numbers appear throughout physics, right? So we have speed of light, we have the strength of gravity, strength of electromagnetism, all the quantum sort of numbers, etc. They're all there. And so a couple of questions you could ask yourself. The one that fine tuning comes from is, what would the universe look like if these numbers were different? Okay, so remember, that's the starting premise. And so I've got my mathematics. I can vary the value of the speed of light. If I wanted to, my equations, I could make it 1 meter per second, and I can see what the consequences of that would be. And so this is the game that we've played for a number of years now with the laws of physics. Let's adjust the parameters and see what the consequences are. And generally, what we find is that the consequences are disastrous for the universe. And what we mean by that is that very quickly you can erase complexity from the universe. And so if you think about it, we're sitting here chatting. What we have discovered over the last 100 or so years is that we, of course, are molecular machines. We are built of atoms, we're built of smaller pieces. For us, carbon is very important, but so is iron, etc., etc. So we are a reflection of the existence of the periodic table. And if I adjust my laws of physics and I erase the periodic table, then the chances of any complexity and therefore life arising quickly vanishes. So if you play around with the fundamental constants and a few other values to do with the universe, you quickly erase the potential for any universe to host life. So the question then comes back to, right? So if I look at the values that we have here that allow us to be here, why does our universe have those particular values? Because if there were other values, we wouldn't be here having this conversation.
And I understand that there's fine tuning for the existence of the universe versus fine tuning for the existence of life. And there is a subtle difference there.
Well, there are many levels of fine tuning, right?
Right.
You can look at this from lots of different perspectives, right? So there's a question of fine tuning for life in terms of the kind of life that we are, or the fine tuning for the general properties of the universe, etc. So it's all sort of in one overall subject. Part of the problem that you have when discussing fine tuning, you find that people grab bits from here and bits from there and jam them together without really defining what it is they're talking about.
But now, I know you do this in the book. Let's do it very quickly here. You need to define life, or how you're going to measure life, how you're going to say that the conditions are necessary to support life. Life has amazing resilience. We talked a little bit about this last week, what the resilience of the life forms that we know about. Life is able not just to survive, but to thrive over a wide range of temperatures and pressures, electromagnetic and radioactive energies, in the presence of all kinds of chemicals and pH levels and oxygen levels, from desert conditions to ocean conditions. It just seems to survive and thrive under all these conditions, and that's just the life here on our Earth, the only planet that we've been able to study life on. But the question then is, could there be other ways to survive? In addition to the life that we know of that has this amazing resilience, maybe there's completely other ways to live, to be alive. And we use the example with Dr. Luke Barnes. I just provocatively said, maybe there's a life form that doesn't even have physical bodies and works with magnetism. So how can we talk about fine-tuning for life if we really don't know enough about life, and life is so resilient, it seems to thrive everywhere?
Well, there's a couple of topics there. Firstly, I agree that life is generally resilient, but if I pop you onto the surface of a star or any other life form, I'd like to see how long you can survive those kind of conditions, right? So we are resilient. I'll give you that. So let's think about this. So we have to be very careful that we don't start to play the sci-fi game, right? What if life is composed of stars that have become intelligent or something like that? We have to play this game within the realm of physics. So yes, I agree that life can be based upon quite different structures or chemicals or whatever reactions that compared to our life here. So we could have that happen. But again, we have to go back to remember that we are a reflection of the periodic table. And life has thrived on Earth because of the abundance of carbon, etc. And if we erase the periodic table, then there's no prospect of carbon life, silicon life, or whatever.
And I'll just jump in very quickly, because I'm just realizing there may be some listeners who don't know what periodic table is. I mean, they should. We learned it in high school. But just in a minute, tell us, what is a periodic table?
Oh, okay. So the periodic table is essentially the listing of each of the different kinds of atoms that we have in the universe. So they're known as the elements: hydrogen, helium, lithium, beryllium, carbon, etc. So it's the collection of elements from the lightest to the heaviest. And so in terms of natural elements, you go from hydrogen at the start, the lightest element, down to uranium at the end, which is the heaviest element. Plus then we've now got heavier elements that we've created in laboratories and nuclear explosions, etc. So it's the collection of basically Lego building blocks from which you can assemble things in the universe. So if we're surrounded by an atmosphere of nitrogen and oxygen and carbon dioxide. At their base level, oxygen is 2 oxygen atoms, nitrogen is 2 nitrogen atoms, carbon dioxide is a carbon atom, 2 oxygen atoms. You build up molecules from those basic parts. Inside your body, you are a molecular machine. Your DNA is constructed from individual atoms, etc. In fact, everything to do with you at base level is atoms.
And is it true that I'm the layperson in this discussion, just so you know, a long interest in science, but not a scientist by any means. Is it true that all of these go back to hydrogen, that everything is a permutation in a sense of hydrogen?
Yes, so this is one of the most wonderful discoveries of like the early 1900s. And actually, one of the people who has been forgotten in this story was a scientist called Moseley. He would have won a Nobel Prize if he hadn't been taken out by a Turkish sniper in Gallipoli in World War I, right?
Wow.
I mean, there was the first realization that we have different elements. And then there was a realization that the elements are actually made of smaller bits and pieces. So the two fundamental pieces for atoms are the proton and the neutron. And so a hydrogen atom, the nucleus is essentially just a proton. Helium is then you take two protons and two neutrons, and you now have the element helium. So you've got two protons, and then you go to three protons plus neutrons. You have lithium, four, etc., etc. You work your way all the way up the periodic table to 92 protons, and that's your uranium nucleus. So the reason why the periodic table, in my mind, is so beautiful is that before that point there was chaos, because how do you compare sulfur to mercury, right? I mean, they just seem such different substances. But when you realize that all it is that it's Lego blocks stuck together, and you want to make the next one, you put in another Lego block. I think that's beautiful.
It's almost like alchemy in a way. I know it's not alchemy, but in the sense that, the idea of turning lead into gold kind of thing, the idea that you can just combine different. Go ahead.
Absolutely. And in fact, what we have going on in laboratories around the world now is people trying to make heavier and heavier elements. And of course, you know how you do that. You basically try and jam more of those building blocks in to build your heavier elements.
Yeah. Wow.
So I'm glad that you've defined it that way. It being the what you mean by fine tuning for the presence of life. You're referring to it as the presence of all these chemical constituents, these atomic particles, carbon, nitrogen, oxygen, all the way up to iron and beyond. As opposed to, and here's the point that I'm going to, some people will talk about fine tuning for life, but they'll be referring to things like the wavelengths of light that the sun gives off, or the presence of the moon, or the gas giants, Jupiter and Saturn. They'll talk about Earth's tilt on its axis, all these different things, and that's not fine-tuning for life. Those are examples where life is fine-tuned for the conditions.
Oh, that's right. This is where things become somewhat murky. You can talk about, why are my bones strong enough for me to stand up on planet Earth, right? I mean, there's no surprise there, because, I evolved on this planet. Now, I do lean towards the rare Earth hypothesis, that the conditions on Earth are not essentially the average kind of conditions you will find on planets around the galaxy. But that doesn't preclude life being out there on other planets, right? It's just that I think that Earth's properties are peculiar in the sense, as you mentioned, the tilt and the wavelength of light and all this kind of thing. They do play a part, but you could get life elsewhere that harness different kinds of things.
Right. I mean, for example, I know that they're looking to see if it's possible for life to be on one of the moons of Jupiter, I understand. And if they find that life is going to be finely tuned for the conditions that exist on that moon, which are nothing like here on Earth, and those organisms probably wouldn't survive here.
Oh, yes. I mean, this is life on other planets in the solar system is kind of interesting from a number of reasons, right? So the big question is whether that life will be similar or different to ours in terms of the basic structure, because we know that rocks have traveled around the solar system. Earth has been struck by rocks that have sent other rocks to other planets. We have rocks from Mars on Earth. It's all gone around. And so the question is, if you go out there and you find that it's got a basic structure similar to life on Earth, that would suggest that life has spread around the solar system. The real big interesting question is if it's going to have a different structure, if it's not based upon, the kind of genetic structure that essentially all life on Earth has, that then things get interesting. But yes, I mean, the entire field of astrobiology has exploded over the last few decades. And one of the key questions that they ask is, given a planet with these conditions, what pathways could I imagine life taking to take advantage of those pathways?
Now, this is another story that I hear often when I read on this topic of fine-tuning or, astrophysics, astrobiology, that sort of thing. They'll talk about this story of Fred Hoyle, and they'll talk about, these are technical terms, resonance in the carbon atom and resonance in the oxygen atom. Do you want to tell us a bit about that story?
I can try. I mean, it's an excellent story, and at some level, it has almost become myth. It's in some certain aspects, so you have to be very careful. I mean, there's a nice review article by, I think it's Kragh, Kragh, that talks about the actual things that happen. So let's set the scene. So Fred Hoyle, I must admit, I don't have a lot of scientific heroes, but Fred Hoyle is one of them. He was a bit of a maverick back in the 20th century. So he came from the north of England, and ended up becoming this leading astronomer and cosmologist. So he had really deep insights into the universe. He famously was one of the ones that worked out how stars transmute elements, right? He worked out that stars produce, you burn hydrogen to helium all the way up through oxygen, all that kind of stuff. And he was also famous for objecting to the notion of Big Bang cosmology, that there was a birth to the universe. So he had his own idea, the steady state universe.
When they refer to steady state, they're getting at the idea that the universe has always been. There was no beginning, there will be no end, it just always is and was.
And Fred enjoyed a fight, so he was known to have somewhat contradictory views to some people on certain things. So the thing is with Fred is that when he was wrong, he was often very wrong, but when he was right, he was extremely right. So I've always loved that, and I think that is the essence of a good scientist, is that now and again you have to put your neck on the chopping block with your ideas, right?
Right. And before we get too far away from what you said about him making a comment about the Big Bang, he was initially against the whole idea. And if I understand the story right, that was completely on ideological grounds. He didn't like the idea that played into the creationist hands.
Oh, well, again, this is now more myth than story. So as I point out that it wasn't that he initially rejected the Big Bang. He never accepted it. He died in 2001, and I saw a talk by him in the mid-1990s where he was still banging the drum essentially for his modified steady state. Now, it wasn't just Fred Hoyle who had put steady state on the table. He had a few colleagues, and what they were doing, in my mind, was completely sensible, right? A modern cosmology is built on something called the cosmological principle. It's an idea where, we look around in the universe and we see the universe looks the same in all directions, etc. The cosmological principle is something that students are taught, but what it really contains is a statement about the mathematics we think control the universe, that our universe contains symmetries, and these symmetries are these powerful things in physics. And so the fact that the universe looks the same in all directions means we have these symmetries, and it's from those symmetries that we build up the entire mathematical structure of our universe, okay? What Hoyle and his collaborators were doing is saying, let's add one more symmetry. Let's just, as well as it looking the same in all directions, why don't we add the symmetry that it looks the same in time, that it looked the same yesterday as it does tomorrow? So you put that in and you end up effectively with a steady state cosmology. The problem is, of course, is that the observations that came out, especially through the 50s and 60s, showed that the universe was different in the past, right? The universe was a different place. And so that symmetry that they had grabbed hold of didn't apply. And then the rest of Fred's career was trying to point out how all these observations were either wrong or could be jerry-rigged into his ideas, etc. So that's, I think it was a good idea. Where he went wrong is that once the observational evidence became overwhelming, he should have done what good scientists do. There's a phrase in writing, kill your darlings, which means, you've got to be willing to let go of your idea if it's going to improve the overall book that you're writing, etc. And that's what a good scientist needs to do. That you might have an idea that you think is wonderful, right? But if the universe refuses to play ball, then you've got to bin it, because you're not playing the science game anymore.
So have creationists taken that story and changed it? Because as I understood it, it was because he didn't like the idea that it meant the universe had a beginning, and we don't want that because then the creationists are going to run with that. Is that then a creationist myth?
No, I don't think it's. I think there's a lot of myths involved here. I think that was part of it, right? So the history is that you had Hubble and Einstein and all those guys working in the early 1900s, and one of the key players there was Georges Lemaitre, okay? And Georges Lemaitre was a Belgian cleric. He had a religious background, and he also did general relativity and cosmology, right? So he had his religious side, plus he also had his physics side. And he took the data from Hubble and said, look, we live in an expanding universe. This is what Hubble's shown. If we wind that back, there is a start, right? So it's a simple statement. But the problem is that he was wearing a dog collar. I don't know. I don't know if Belgian clerics wear dog collars, but you know what I mean.
Yes, yeah.
Is that he had that background now? But what if it wasn't Lemaitre that made that statement? Okay, so there was also another guy working around a similar time, Alexander Friedman, who was in Russia. He had been working through the maths. What if he had made that statement, right? So, he was living in Soviet Russia at the time, famously kind of atheistic country. Would the Big Bang have lost all of that baggage straight away? I don't know, but the problem is the Friedman died in the mid 1920s, and so he didn't make that connection. It was Lemaitre. And now, also, when Hoyle made those kind of statements, and I'm sure that he did, what's often left out is that he was actually mates with Lemaitre. He knew him quite well, and so there were these statements that this is creationism or religion being smuggled back into cosmology, but if we could play that game, erase everybody's memories and start again, and we gather the data, just look at the data and the mathematics, then that's the conclusion that you come to, right? Is that we live in a universe that has a start. And of course, it's the norm now that that's the universe that we live in.
Now, we've gotten quite a ways away from the whole resonance of carbon.
We were talking about carbon.
Yeah, and let me just let the listeners know why I'm so intrigued with this. It's because Hoyle made this famous statement. He was looking at the resonance of carbon and other things like oxygen, and he said, and there's dozens of these examples of these, but this is one in a very prestigious scientific journal, Annual Review of Astronomy and Astrophysics. He said, a common sense interpretation of the facts suggests that a super intellect has monkeyed with the physics, as well as with the chemistry and biology, and there are no blind forces worth speaking about in nature. So this is why I want to hear more about this story.
Okay, so the story is I like the story. Again, you have to be careful of the myths. So Fred Hoyle, as I mentioned, was part of a key group that worked out how the elements were built up in stars, right? So the universe starts off as basically being hydrogen and helium. That's what comes out of the Big Bang. And then stars form and stars burn hydrogen and helium into the heavier elements, etc. And what you can do is you can calculate the rates at which those elements form, right? So you basically, we know how hot the center of a star is, so we know how dense it is. You can calculate the nuclear reaction rates, and you can calculate how light elements burn into heavy elements, etc. And when Fred Hoyle and there were others dealing with this question about the same time, when they were looking at the formation of carbon, there appeared to be a problem. And the problem is that to make carbon, you've got to go through the earlier steps of hydrogen to helium, lithium to beryllium, and etc. But it turns out is that the lighter nuclei, especially beryllium, are very fragile. Right. So if you imagine that you're trying to make these things in stars, what's happening is you create these things, but then you tear them apart. You create them, tear them apart, etc. This is what happens with fragile nuclei. And so Fred basically said, well, this is weird because this suggests that stars should be very inefficient of getting through that first step of lighter elements into carbon, right? But he said, oh, when I look around the universe, all I see is hydrogen, helium, and mainly carbon and oxygen. They are the next two most common elements. And so he said, well, if this is really the case that there's carbon in the universe, then there's something missing in that step from the lighter elements into carbon. And what he realized is that that step is that there is a little window which allows you to turn the lighter elements into carbon, whereby things come together, they stick into effectively carbon. You would expect that carbon to be ripped apart again, but there's a magic window where that carbon sticks together, and it basically, let's just put it in simple terms, it sticks together, and instead of ripping itself apart, the energy that would have ripped it apart has now become basically spin. It come together in just the right way that it sticks together as a spinning nucleus, and it stays as carbon, right? So this is what this resonance is. It just means there's a window whereby instead of being ripped apart again, it manages to stick together. And he said, well, this is weird because when I look at the carbon nucleus, and this is what a lot of nuclear scientists were doing at the time, is trying to understand the nuclear structure of carbon, that there was no window there, right? There was no window in the right place. They hadn't found one. And the story goes is that he went and he badgered people in a laboratory to look at a particular energy level, this 7.6 MeV level, etc. And they went there and they found it. And so this is explained how you can turn the light elements into carbon. Now, part of the myth involved there, and I think I'm trying to remember back to this article by Cra, is that it wasn't completely missing, that some people had suggested this energy level was there. And so it wasn't like what's the right way of putting this? It's not like there was no hint that this energy level was there. And the problem that you have with science is messy. And I don't know what Fred Hoyle actually knew before he made his prediction, if he knew there was already a hint or not. But the famous prediction was this energy level was in the right place.
But why, again, I said that you could get a quote like the one I read. I found many of them. He would refer to a super intellect and monkeying around with the physics, that it was a
Look, I didn't know Fred personally. I've been in a room with him, but I don't think that he was really a theistic kind of person.
Oh, not at all. That's why I'm puzzled why he worded it that way.
Yeah. I tell you the kind of person that he was. He was a person that really liked to wind people up. And so, but I think, as I said, he had provocative ideas that he put them on the table. And if you can have a provocative idea, you may as well be a provocateur.
Yeah.
And so what he meant in that phrase, and I can't read his mind, etc. But I think what he was pointing at is that this is interesting, rather than saying that it is necessarily a super intelligent being of one kind or another. It's that this is interesting and needs some understanding. That's the way I would read it.
How about yourself now? We're talking to you. I'm really intrigued to talk to you because you don't hold a theistic worldview, and yet you see design. You talk about this fine-tuning in the cosmological astrophysical data. But doesn't design or fine-tuning require a designer and a tuner? Those are active. Go ahead.
Well, no. You've just conflated a few terms there, and I don't see fine-tuning as design.
Okay.
All right.
So I'll drop the design, but how about tuning? Yeah. Because that implies to me a tuner.
Well, it does, because when you want to fine-tune a piano, you bring in a piano tuner, right? But the thing is from my point of view, is that I see this as a physics problem, in the sense that if there is fine-tuning, I want to understand that in terms of the physical laws. Why do we have the physical laws that we do? And as Luke and I wrote in the book, is that one way you could look at this is that there's a fine-tuner. And if that's your philosophy and that's where you're coming from, then that's yours. But for me, the question is that if it has the appearance of fine-tuning, why does it have that appearance in a physics context, right? You don't need a designer. You need a physical mechanism that gives you fine-tuning. So that's my viewpoint.
Okay. So I mean, one thing that I was going to ask, and I've been reading your book, by the way, and I'm really enjoying it, although it's breaking my brain. But and I know for you that's probably humorous because it's probably kindergarten level physics. But for me, it's been challenging, but I really have been enjoying it, and it intrigues me to want to learn more about physics. I guess one of the things I find frustrating is that biology is something that, I don't know, I can follow, I can kind of understand, I can even read a biology textbook and kind of. Physics seems to have this barrier, though, unless you're at a certain level of math and so on, you really can't understand it. You just have to trust people like yourself. You know what I mean? So help me with that.
Okay. I think one of the things that's happened with physics, and I think this is something that has upset a lot of people, is that physics has moved away from what you would call common sense. Right. I mean, a lot of people understand the physics of Isaac Newton because it's all to do with a horse pulling a cart, and we can all imagine that, right?
Yeah.
But then when you get into the 20th century and the worldview of physics started to radically change, right? I mean, it started in the 1800s. I think even Maxwell with electromagnetism, the physics took on this now almost ethereal kind of thing about magnetic fields and electric fields, etc. When you get into the 20th century and we then start to talk about the realm of the atom, where the rules of Newton no longer apply, then for most people, the common sense that they thought they understood the world with goes out the window. And I have to say to you, well, an electron is a little object and it's a ball, but sometimes it's a wave and it does weird things around atoms. And then similarly, when you go to the large scale and we talk about relativity and the expansion of the universe and all this kind of stuff, we say to you, right, you have to throw away your common sense to understand this, and people don't like that.
Yeah.
But the problem is that if you don't throw away that common sense, then you can't deal with the universe and the world of the subatomic. And we know that these maths, even though they seem absurd and just nothing to do with everyday life, they work, right? This is the thing. Your mobile phone works because of quantum mechanics and relativity. And if we lived in the classical world of Newton and Maxwell, we wouldn't have mobile phones, right?
Okay.
It would be a very different kind of world altogether. So I think the issue a lot of people have with physics is that it's mathematically based. And maybe that's because we're doing the easy stuff that we can write down mathematics to represent it. When you talk about biology and you talk about processes in biology, there's not often a lot of mathematics that carries that along. But in physics, though, to go from step A to step B without mathematics, it's no longer physics anymore if you're trying to do that. So I think that's often the tricky point for people.
So it almost brings up the issue. Then what is fundamental reality? Is it mathematics? Is that even behind? Is that even more? Is that even more fundamental than physics in a sense? Right?
Okay. So I'm going to give you the Richard Feynman response. Right?
Okay.
What answer would satisfy you? Right? Because we the fundamental nature of reality, I don't think there is a single answer. We can just keep going down. I mean, Max Tegmark wrote a book a decade or so ago now called The Mathematical Universe, where he basically says that yes, at the base level, we are all representations of mathematical calculations churning away somewhere, right?
Right.
That everything is just a mathematical calculation. And you think, oh, okay, so that's reality. And then you think, but that's got nothing to do with my everyday life. Are you happy to find that? Yeah. And
right.
it's a similar thing, right? It's like
you're
made of atoms. Okay, you know that, but does it do anything? I mean, you know that it's there. So so you have to choose what answer satisfies you at some level. And I'm not adverse to even crazy ideas like Max Tegmark's idea that it is churning mathematics, etc. You still have to ask yourself, well, what do we gain by knowing that, right?
Right.
And what's the explanatory power, etc.
Right. So it does bring us around to why do physicists care about fine-tuning? Why do they care? We have these numbers. We know they can't be different to have the universe we inhabit. And we know that we don't calculate these numbers. They're not the end of some string of math. They're a given. Okay. So what? Well, like, why do we need to know? Why do we need to know anything else?
Okay, so there's a couple of things. So firstly, let me just clarify. You said, why do physicists care? And I'll point out that the vast majority of physicists don't care. Right?
Okay.
So the vast majority of physicists work in solid state physics, designing devices and all this kind of stuff. So there's a particular viewpoint that some have is that this is the universe we have, and I will work within the rules that the universe has given us, right? So here's our laws of physics. Can I work on the next level of computational chip or quantum device or whatever? I can work within those rules. And then others say, right, they ask the question then, why these values? And so there's more than one answer, right? So to some people, there are these values and these values only, right? And it doesn't make sense to ask a broader question, right? That there is no answer. So some people sort of think that if I keep doing the maths and work harder and harder, eventually we'll find that the mass of the electron is some combination of pi and e and the usual mathematical things, right? So maybe we'll get there. But others say, well, what if there's something deeper, right? What if there is a selection process, i.e. the universe could have had different fundamental constants, but we've got these ones. So what's the process whereby does the universe generating device try different values? Okay. Or does it only produce single values, i.e. universes like this? And if it does, then what's controlling that? So it's that sort of wish to go deeper, to understand not just the universe, but where did the universe come from? What brought the universe into being? What could it have been differently, etc.? And again, you have to remember this is a subset of physicists, and often it's not necessarily their day job. So some people get very very angry. Then it's like, why are taxpayers' money being spent on people wondering? And what you don't realize is that nobody spends 100% of their time really focused on this. We have other things that we have to do. Teaching, university administration is one of them. But it's one of those questions that motivates you to look deeper. That's why I'm interested in it.
Do you think there's at least a possibility that discovering some of those things you're talking about would have actual implications for physics? In other words, we could predict different things. Could it result in practical applications for physics?
Oh, yeah, because I think part of this story, part of the looking for this solution is related to the issue that we have in fundamental physics at the moment, is that we have two key theories: the quantum mechanics of the universe of the very small, general relativity to describe the universe of the very large. They are two different mathematical structures, and they do not play well together. So, and physicists are very unhappy that we have to have two textbooks, one on quantum, one on relativity. And what they want is one, right? They want the theory of everything. And, it's the lack of a theory of everything that is stopping us from looking at the initial moments of the universe, right? We can look back only so far, but we can't see precisely where the universe came from. And if we crack that nut of the theory of everything, I mean, I can't predict exactly what we're going to have, in the same way as that Maxwell couldn't predict when he, showed that light was an electromagnetic wave, that we would now have radio communications out there. I'm talking to you, signals going through optical fibers, bouncing off satellites, etc. You don't know what's going to come out of it, but at some level, it's going to be wonderful and terrifying. Right? Yeah. Because you get advances and you get weapons.
Yeah.
It will open lots of doors.
Okay, I'm going to bring us back to the topic at hand.
Oh, yes.
Yeah. We've been talking about this fine tuning, and we talked about how I asked the question, if you're talking about tuning, then there's a tuner, and then you suggested, no, we don't need to go down the road of theism. In the process of answering Scott's question, you used the word selection, that this machine selects values. What would be the non-theistic explanation for all of this tuning that doesn't require a tuner and that selects things? What are some non-theistic explanations?
Okay. So, I mean, there's a couple of semi-crazy ones, which a lot of people are fans of. I mean, there is one where there's a tuner, but the tuner it's the simulation hypothesis that we again, this idea that we are really just a computer program that's running, and some creature in another dimension above is running us. And of course, what they can do, and this is where it gets kind of bizarre, because I have my PhD students, they generate their own universes, right? That's what they do when they do their PhD research. They simulate universes. They're very coarse-grained, and they don't have planets and things in there. They look at large-scale structure in the universe. But you could imagine, and I think this is something that Elon Musk spoke about a while ago, is that you could imagine that as we increase computer power, that our simulations become higher and higher resolution, more and more physics, etc. And we simulate universes that we think are interesting, right? And who knows, maybe we get to the point where the universes that we generate, that there's the equivalent of consciousness in there, right? And that's the idea that that some people have proposed for our universe, is that we are a simulated universe. Somebody's, maybe it's a grad student in the dimensions above is running us as a little test thing, and they've set up the conditions because something interesting happens, and it might not be us is the thing of interest, right? We might be a consequence, right? It might be oh look, we can create a periodic table in this universe or whatever. So the simulation hypothesis there, I'm not a giant fan of the simulation hypothesis. Sort of hoping that the cleaner doesn't come in and pull the plug out of the wall of the computer. So my favorite hypothesis is the notion of the multiverse, that our universe is one of many universes. I think it seems kind of reasonable that if whatever happened bothered to make one universe, why stop at one? Right? So it generate universes, and there are different ways of producing a multiverse, right? So there's mechanisms for generating universes within universes, etc. And that there's some process when you birth a universe. The universe starts off in this very sort of pure kind of state, very high energy, very, very pure kind of state. And then it cools. And as it cools, the universe evolves. It essentially, the properties of the universe crystallize out of that kind of pure state, right? And so for our universe, that we have our hot Big Bang, where everything originally is like superheated particles, etc. As the universe cooled down, it condenses into the matter particles and then into stars, etc. But you could imagine that in those initial instances, that one of the things that comes out of that cooling process is the laws of physics themselves. And there's a bit of a randomness to exactly how you get your laws. So one universe might have slightly different laws to our universe. Other universes might have radically different laws compared to our universe. And so in this multiverse kind of scenario, you produce a huge number of universes, 10 to the 500, right? An infinite number of universes, whatever. And they've all got different laws of physics. And then across the multiverse, most of those universes are going to be dead and sterile because they ended up, they didn't win the physics lottery. They ended up with no complexity, no life, they're empty, etc. But there will be islands where the conditions are right for complexity, for something equivalent to a periodic table that allows complicated things to happen. And in some of those, life will be one of those complicated things.
So I want to talk about a couple challenges to this multiverse explanation for the fine-tuning. And you nudged on one of them. You talk about winning the lottery. That'll be the second one I want to talk about. But first, people have said, look, we don't have evidence of a multiverse. This is just a notion. We get hints of it from string theory and from inflation theory, but we have no evidence for it. So now it starts to sound like a faith statement that we say we appeal to the multiverse.
Well, but again, I will restate my statement. I said my favorite thing is the multiverse hypothesis, right? It's not a theory. It's a hypothesis. It's an idea. So people seem to forget that science has stages, right? You propose your hypothesis, you look for your evidence, and if the evidence is in favor or against that, the multiverse is at the hypothesis stage. That's where it is. So let me give you an example from 20th century physics, right? So de Broglie, who was a French physicist, he proposed that matter could behave as waves, right? He had a really short PhD, got a Nobel Prize for it, etc. Matter, because people have said, well, waves can behave like matter. And he went, oh, well, then matter can behave like waves. And he wrote it up. Now, imagine he had submitted his thesis, right? Theoretical thesis. And the examiner went, well, there's no evidence that matter can behave like waves because that didn't come until somebody did the experiments afterwards. Therefore, your thesis, we have to put it in the bin because there's no evidence there. No, science is you propose a hypothesis, you then go looking for evidence. Now, the multiverse hypothesis is still a very loosely formed hypothesis. There's no single multiverse idea. There are various ideas. Some of them have some mathematical structure. Others are still ideas. And they have not condensed into that notion of how do I test this? So I think it's too early to stamp your feet and say there's no evidence. Therefore, you're not allowed to even think about the multiverse, which is what some people have done. I've seen this happen more than once. So yeah, there's not evidence, as I said, but it's a hypothesis, and it's my favorite hypothesis. If evidence comes along and says to me, right, there is no multiverse, then I do what a good scientist does, and I say, well, okay, I was wrong on that. But I think we have to develop the theories, look for the predictions, and then test them against our observations. And we're just not there yet.
So is one of the issues with the multiverse hypothesis, because I assume what you're saying is it's a scientific hypothesis. So you could of course have non-scientific hypotheses. So does it meet the criteria of a scientific hypothesis? In other words, is there a way to get experimental evidence? Like Einstein's theories, of course, it took Eddington to go out and prove with the observational data the idea that light bent around planets, right? That was right. And apparently, from what I've read, Einstein wasn't very impressed because he said, well, I solved that problem years ago. So, I don't know why you're bothering with observations. But
the myth and the reality are slightly
different.
Okay.
Well, I watched the movie. Movies don't lie, do they?
Yeah.
But is there a possibility of getting observational evidence for a multiverse? Like, is that
people have proposed various experiments that we could try. I mean, one of these was proposed by Roger Penrose, who's now a Nobel Prize winner, right? So he has this notion that if you have a multiverse and it's producing multi-universes, etc., that you could get universes in collision. A universe here could bump into a universe next door. And the question is, where would you see a signature of that bump? And of course, in our universe, we have this thing called the cosmic microwave background, the leftover radiation from the Big Bang. And he suggested that you could see a scar of a collision written into that cosmic microwave background radiation. And he thought he had seen something like a signal that shouldn't be there. Other people have gone back and looked and said, no, look, it's not there. The thing that you thought you had seen. So people are proposing ideas. But again, I mean, I feel that multiverse ideas are probably more similar to where electromagnetism was at the start of the 19th century, right? Where people had said, oh, these magnet things are strange. And look, there's currents that can make frogs' legs jump, etc. And it took a long time until Maxwell could gather the pieces and come up with the mathematics that was needed, right? So we could be a century away from even having a robust set of mathematics to get the predictions, right? To test the multiverse. But to go back to your initial premise, I think, yes, this is a scientific hypothesis in the sense that it could provide a solution to a perceived problem. And there's nothing to say that it won't produce predictions once we have the mathematics. Now, we could, of course, derive the mathematics of the multiverse, and it might say that, yes, there are other universes out there, but they are disconnected and we will have no contact, etc. And they may as well be unicorns at the bottom of the garden. So then you sort of go, right, well, I can't test this. Is this science? Then you worry. I think it's too early to get spooked by these ideas.
Okay.
So I said that there was two challenges that have been put out to the multiverse theory, and the second one was going to be one that I said, you've already hinted at it. It has to do with, basically with gambling. You may have heard of the gambler's fallacy or the inverse gambler's fallacy. So do you want to explain what it is and how you push back on that?
I'll tell you what, I'm going to let you explain what you think the gambler's fallacy and the inverse gambler's fallacy are, because I have Phil Goff, who's been pushing the inverse gambler's fallacy. I'm hoping to be catching up with him later in the year. But I think it's a complete furphy. But please, let's go with Let's go with your interpretation to start with.
Okay, I'll do so. And I want to go through a little bit slowly because I'm also trying to keep the audience up with us. So let's start with this gambler's fallacy. It's the chance of the random outcome happening, let's just say the roll of the dice or a winning poker hand. I'm committing the gambler's fallacy if I think the chance of that happening is influenced by whether it's already happened previously or not. Mm. So, for example, if I roll the dice a couple times, 5 times, and I keep getting double sixes, every time I'm getting double sixes, 5 times in a row, and we demonstrate that the dice are not weighted, they're regulation dice, when I get ready to throw the dice a 6th time, the gambler's fallacy would have me predicting that the 6th roll will either definitely be double sixes again because I'm on a roll, or it definitely won't be double sixes again because I've already exhausted that possibility 5 times. Either way, I'm forgetting that the probability of rolling double sixes the 6th time has nothing to do with what already happened the 5th and the 4th and the 3rd time, as long as the dice aren't loaded. So that's the regular fallacy. Now, can I take another minute to explain the inverse one? because it is a bit different. This is what happens if you roll the dice a double, and you get double sixes 5 times in a row, and then you do get on the 6th time a double six again, and so you conclude that because that's a very unlikely possibility, at that moment in time when I threw the dice for the 6th time, there must have been millions of other people in casinos around the world also trying to get double sixes, because if there's lots of people playing throughout the world, then it's more likely that someone will get the numbers right. And so that's the inverse gambler's fallacy. The gambler's fallacy says that me getting those double sixes is influenced by what I've already rolled in my casino, and the reverse gambler's fallacy says that me getting those double sixes is influenced by whether other people in other casinos were rolling their dice at the same time. And if you know how probabilities work, me getting double sixes has nothing to do with either scenario. So that's the inverse gambler's fallacy. And people say, this kind of says something about the multiverse theory.
Yeah, I mean, I think what people are saying. So I think what Phil is saying, and the problem with, okay, I'll be careful with my words here, right? So Phil is a philosopher of science, and philosophy arguments, of course, can get very messy very quickly because it all becomes down to definitions, all this kind of stuff. So essentially what we're saying is, for the inverse gambler's fallacy for our universe, it's just that effectively what we're saying is that we have the properties of the universe that we see around us, and they are the way they are. And there's no reason to think that it wasn't essentially blind luck that a single universe was created and it had the right properties. We don't need to hypothesize that the universe was churning out universes left, right, and center and had to produce 10 to the 500 universes, for us to have a chance of existing, right? And I don't understand, I still don't understand from Phil how this can basically rule out a multiverse hypothesis. So again, you said multiverse theory earlier on. It's hypothesis, just to be clear,
sorry.
right? No. Again, because this leads to many arguments. And a multiverse hypothesis is not, you need an infinite number. You could have 2 universes. That's a multiverse hypothesis, right? Or 3 or 5 or 7, anything that has more than one. And I've still not really fathomed, even though Phil has got lots of examples about you come across a talking monkey in the jungle, etc. That it really says anything limiting about what a multiverse hypothesis really would say. That the fact that we have these properties, I think, is either consistent that, yes, maybe we were lucky. Maybe there was only one universe and there is a random procedure and we got the roll of the dice. But it doesn't rule out that the other process, that there are lots of other universes being created, is not ruled out by that notion of the inverse gambler's fallacy. And unless, again, I'm hopefully going to see Phil later in the year, and we'll go for a beer in Durham, and we'll thrash this one out. But I'm not buying that this is really ruling out the hypothesis.
Can I ask, what instead of having to appeal to a multiverse, what about just a cyclic universe? In other words, we expand, we crunch back into an infinite singularity again, and that explodes out. And next time it happens, there's nothing. We have a neutron universe, and that expands and goes back. In other words, you have the cyclic universe that cycles infinitely. Eventually, it's going to hit on our universe, right?
Yeah,
it has to, right? If you give it infinity, it has to. Is that a possibility, or is that not a possibility?
What you've just proposed is just another multiverse.
Well, right? I guess it is. Yeah.
So instead of them being parallel, you've just got them sequentially.
Right. Okay. So, fine. Yeah.
You've just proposed a brand new multiverse. Welcome to the club. Right. Make sure you pick up your goodie bag on the way out.
Write a paper, Scott. Write a paper.
Yeah. I have a feeling it wouldn't be taken seriously. Yeah.
There is actually an idea not too far away from it called the ekpyrotic universe, which Paul Steinhardt and Steinhardt, and I've forgotten who the other guy is.
He's looking for the name Neil Turok. Paul Steinhardt and Neil Turok.
Anyway, so there they have a pair of universes that basically collide over and over, and each collision is a new Big Bang, right? They don't do a purely cyclical one because There are issues around entropy, which we could spend another hour talking about, but they have a mechanism for basically getting around that by crashing these things together. So one of the reasons that they proposed this idea, you've got these two universes crashing, is that the notion of our universe, that we had this early epoch of inflation in the earliest stages of our universe. So there's an aspect of that called eternal inflation, which is a multiverse idea. It produces universes in this expanding inflation. They propose this to get around that notion that you'd be creating all these universes in a multiverse. But the weird point is that to get around it, they have two universes, which is a multiverse. You have more than one universe, right? So you can see that the entire sort of landscape of multiverse hypotheses, it's not a single idea. You can propose various things that fit with this notion that the universe is taking, random shots at creating universes, and we're in there somewhere.
Right. Okay.
Okay, gentlemen, we've gone long. You've got a date with your wife, coffee and baguettes on the streets of Paris.
Yep.
Geraint, is there anything that you want to say before we finish? Anything that we haven't covered or that you want to summarize or clarify?
Well, look, we've covered a lot of ground there.
Yes.
The thing that I would just like to remind people, when I wrote that book with Luke, we wrote it for a purpose. And the purpose is that we had both seen aspects of the fine-tuning argument, etc. And what we had seen is that you had two camps shouting at each other from the hills, right? So you have the theistic camp and the atheistic camp, both basically saying that the other side are a bunch of idiots. And what we wanted to do is we wanted to write a book whereby we could lay out fine-tuning as a scientific problem, right? That's what it is. It's a scientific problem, observations, and in the last part of the book, we wanted to give the perspectives, the theistic, the atheistic, multiverse, etc., etc. And I think that that's the way that people need to go forward. Rather than saying, my camp is right because, and your camp is wrong, that understanding the problem and then working through the various hypotheses, whatever they may be, is the way to go here, right? So I'm just, I know it's a bit kumbaya, but but I hate the fact that there are camps that shout at each other, and I know that really that there are small groups on either side, and there's a big sea of people in the middle, but it's the loudest voices are the ones on either side. So
Right.
yeah, I just said I enjoy talking about this, and I'm happy to talk with people, whatever their background is. But it's the notion of understanding what the problem is, I think, is important.
Yeah.
Do you have another book in the pipeline?
I actually do. I have a slightly more academic book coming out next year called A New Copernican Turn. It's written with Doru Karuchuse. It's another book where it's science and religion. So he's theistic, and he's writing about how modern cosmology fits in to the theistic version of cosmology. So I wrote about what we know and what we don't know about the universe. So that book should be coming out next year. As I said, that's slightly more academic. And I'll be signing a contract in the coming week on a book called The Shortest History of Reality, where I will be basically writing about some of the things we talked about. This notion that if you peel away the universe trying to find reality, what is it you find as you go through each of those stages? So my guess is that it'll appear somewhere in 2025, maybe 2026.
Very good.
Well, we'll have links in the show notes for the books that you have written. We can't provide links for the ones that you're about to write. But we highly recommend this third one that you wrote with Dr. Barnes. It's a great book. If you're interested in this topic, it's a must-have.
So, thank you very much.
Geraint, thank you for joining us, giving us your time again on your holidays. We really do appreciate this.
Thank you very much. Look, as I said, it's always fun to talk about the universe.
Yeah.
Okay, thank you.
Okay, bye-bye.
Bye.
You've been listening to Recovering Evangelicals with your hosts, Luke Jansen and Scott Dyer. Send your comments and suggestions for new episodes to lukejjansen@gmail.com. Join our private discussion group on Facebook by searching for the Recovering Evangelicals podcast group. Look for the logo that you always see at your favorite podcast catcher and ask to be let in. Subscribe to lukejjansen.wordpress.com if you want to get advanced releases and group posts, or browse through our archive for a full listing of all our previous episodes. And please help the podcast by sharing with a friend and leaving a review at your favorite podcast catcher.